What is a power MOSFET? How does it function and its application? What is a power MOSFET? A power MOSFET, metal-oxide-semiconductor field effect transistor, is a type of transistor specifically designed to handle significant power levels. It is widely used in switching applications and power management due to its ability to operate efficiently at high frequencies and with high currents. Power MOSFETs are a crucial component in many electronic devices, especially in power conversion systems such as DC-DC converters, motor controllers, and inverters. How does a power MOSFET function? A power MOSFET operates similarly to a standard MOSFET, but is optimized for high-power applications. Here's how it functions. The structure of a power MOSFET is designed to optimize its performance for high-voltage and high-current applications. Here's a detailed breakdown of the key components and features of a power MOSFET structure. 1. Terminals. Gate. G. The terminal that controls the MOSFET. A voltage applied to the gate creates an electric field that modulates the conductivity between the drain and source. Drain. D. The terminal through which the output current flows when the MOSFET is in the on state. Source. S. The terminal that supplies the current to the load. In a typical application, the source is connected to the ground. 2. Channel. The channel is the region between the drain and source. It allows current to flow when the MOSFET is turned on. The type of channel determines the MOSFET type. N-channel MOSFET contains N-type, negatively doped, material, where electrons are the charge carriers. P-channel MOSFET contains P-type, positively doped, material, where holes are the charge carriers. 3. Gate oxide layer. A thin layer of insulating material, commonly silicon dioxide, is placed between the gate and the channel. This layer prevents current from flowing directly between the gate and the channel while allowing the electric field to control the channel's conductivity. The thickness of this layer influences the device's performance, including its gate capacitance and switching speed. 4. Substrate. The substrate is the base layer of the MOSFET, typically made of silicon. It provides mechanical support and acts as the body for the device. It can be lightly doped N-type or P-type silicon, depending on whether the MOSFET is N-channel or P-channel. 5. Source and drain regions. The source and drain regions are heavily doped with impurities to create low-resistance contacts for current flow. The doping level of these regions is significantly higher than that of the channel to ensure efficient current conduction when the MOSFET is turned on. 6. Body diode. A parasitic diode exists between the drain and source due to the p-n junction formed by the channel and substrate. This diode can conduct in reverse bias conditions, which is important for certain applications like motor control. Key features of the structure. Planar versus trench structure. Planar structure. Traditional design, where the gate is above the channel. Trench structure. The gate is formed in a trench in the silicon substrate, which allows for better packing density and improved performance, particularly for high-voltage applications. Surface and thermal management. Power MOSFETs often have features to enhance heat dissipation, such as heat sinks or improved packaging designs to maintain reliability during operation. Doping profile. The doping concentration and profiles of the source, drain, and channel regions are critical for optimizing performance characteristics like switching speed and on resistance. This structural design allows power MOSFETs to operate effectively in a wide range of applications, providing reliable switching capabilities and power handling. The operation of a power MOSFET is based on its ability to control the flow of electrical current between the drain and source terminals using a voltage applied to the gate terminal. Here's a detailed breakdown of how a power MOSFET operates. 1. Basic operation modes. Power MOSFETs can operate in two main states. Off state, cutoff mode. Condition. When the voltage at the gate, V_GS, is less than the threshold voltage, V_H, the MOSFET is in the off state. Current flow. In this state, there is no conductive channel formed between the drain and source, resulting in minimal current flow, ideally zero. Characteristics. The MOSFET behaves like an open switch, preventing current from flowing through it. On state, saturation/linear mode. Condition. When the gate voltage exceeds the threshold voltage, V_H, the MOSFET turns on, allowing current to flow between the drain and source. Current flow. A conductive channel forms in the semiconductor material, allowing electrons, in an N-channel MOSFET, or holes, in a p-channel MOSFET to move from the source to the drain. Characteristics: the MOSFET operates like a closed switch, and the resistance between the drain and source, R_S on, is low, enabling efficient current conduction. 2. Control mechanism. The gate voltage controls the operation of the MOSFET. Gate voltage, V_GS, the voltage difference between the gate and source terminals. Threshold voltage, V_TH, the minimum gate voltage required to form a conductive channel between the drain and source. The threshold voltage is a crucial parameter that determines when the MOSFET turns on. 3. Electrical characteristics. On resistance, R_S on. When the MOSFET is in the on state, it has a low on resistance, allowing current to flow with minimal voltage drop and power loss. The on resistance is influenced by the MOSFET's design and materials. Drain current, I_D, the current flowing from the drain to the source when the MOSFET is on. It depends on the voltage across the drain source terminals, V_DS, and the gate voltage, V_GS. 4. Transfer and output characteristics. Transfer characteristics. The relationship between gate source voltage, V_GS, and the drain current, I_D. As V_S increases beyond the threshold voltage, I rises sharply. Output characteristics. The relationship between drain current, I_D, and drain source voltage, V_DS, for various gate source voltages, V_GS. This characteristic helps determine the operating regions, cutoff, saturation, of the MOSFET. 5. Switching behavior. Turn-on transition. When V_GS exceeds V_TH, the channel starts to form, allowing current to increase rapidly. Turn-off transition. When V_GS falls below V_TH, the channel closes, and current stops flowing. 6. Dynamic characteristics. Power MOSFETs have specific dynamic characteristics that are essential for high-speed applications. Gate charge, Q_G, the total charge required to switch the MOSFET on and off. Lower gate charge values lead to faster switching times. Switching times. Turn-on time, the time it takes for the MOSFET to switch from off to on state. Turn-off time, off, the time it takes to switch from on to off state. 7. Capacitances. The operation of a power MOSFET is influenced by its inherent capacitances. Gate source capacitance, C_GS, affects the gate charging time. Gate drain capacitance, C_GD, influences the Miller effect, where the gate voltage can rise during switching due to feedback, impacting the turn-off time. Drain source capacitance, C_DS, affects the drain current behavior. Summary of operation. In summary, a power MOSFET operates as a voltage-controlled switch, enabling or disabling the flow of current between the drain and source based on the gate voltage. Its efficient switching capabilities and low-on resistance make it ideal for various applications, including power management, motor control, and signal amplification. The key operating parameters, such as threshold voltage, on resistance, and switching times, are critical for ensuring optimal performance in practical applications. Power MOSFETs exhibit several key properties that make them suitable for high-power and high-frequency applications. Here's a detailed overview of these properties. 1. High input impedance. Description: power MOSFETs have a very high input impedance due to the insulated gate oxide layer, which requires minimal current to control the gate voltage. Implication: this property allows for low power consumption in the gate drive circuit and enables easy interfacing with digital control signals. 2. Fast switching speed. Description: power MOSFETs can switch on and off rapidly, typically in the nanosecond to microsecond range. Implication: fast switching speeds result in reduced switching losses, making them suitable for high-frequency applications such as switch-mode power supplies and PWM, pulse width modulation, control. 3. Low-on resistance, R_DS on. Description: when in the on state, power MOSFETs exhibit a low resistance between the drain and source, defined as R_DS on. Implication: a low R_DS on leads to minimal voltage drop and power loss during conduction, enhancing the efficiency of power conversion systems. 4. Thermal stability. Description: power MOSFETs can operate over a wide temperature range and are designed to handle thermal stress. Implication: This stability allows them to maintain performance in varying environmental conditions and ensures reliability in high-temperature applications. 5. High voltage ratings. Description: Power MOSFETs are available in various voltage ratings, typically ranging from 20 V to several hundred volts, with some specialized devices capable of handling over 1000 V. Implication: High voltage ratings make them suitable for applications in power conversion, motor drives, and other high-voltage circuits. 6. High current handling capability. Description: Power MOSFETs are designed to handle high currents, often exceeding several tens to hundreds of amperes. Implication: This property makes them ideal for applications that require significant power delivery, such as industrial motor controls and power supplies. 7. Body diode. Description: Each power MOSFET has a parasitic body diode formed between the drain and source terminals. Implication: This diode allows for reverse current flow in applications like motor drivers and helps protect against inductive kickback. 8. Gate charge. Q_. Description: The total charge required to switch the MOSFET on and off, which is influenced by the gate capacitance. Implication: Lower gate charge results in faster switching times, which is crucial for minimizing switching losses in high-frequency applications. 9. Miller effect. Description: The gate drain capacitance, C_GD, can cause the gate voltage to rise during switching due to feedback from the drain. Implication: This effect can influence the switching speed and stability of the MOSFET, necessitating careful gate drive design to mitigate its impact. 10. Voltage and current ratings. Description: Power MOSFETs are characterized by their maximum voltage, V_DS, and current, I_ ratings. Implication: These ratings determine the operational limits and ensure the MOSFET can handle the expected load conditions without failure. Summary: The key properties of power MOSFETs: high input impedance, fast switching speed, low on resistance, thermal stability, high voltage and current ratings, the presence of a body diode, gate charge characteristics, and the Miller effect make them versatile and essential components in modern power electronics. These characteristics enable their widespread use in various applications, including power supplies, motor drives, automotive electronics, and renewable energy systems. Power MOSFETs are versatile components widely used in various applications due to their efficient switching capabilities and ability to handle high power levels. Here's an overview of some key applications. 1. Switch mode power supplies, SMPS. Application: Used in AC-DC converters and DC-DC converters. Function: Power MOSFETs efficiently switch the input voltage on and off to regulate output voltage, leading to high efficiency and compact designs. 2. Motor control. Application: Used in DC motor controllers, brushless DC motor drives, and stepper motor controllers. Function: They control the speed and direction of motors by rapidly switching the current flow, allowing for precise control in applications like robotics and industrial automation. 3. Inverters. Application: Used in solar inverters, uninterruptible power supplies, UPS, and electric vehicle, EV drives. Function: Power MOSFETs convert DC to AC, enabling the use of renewable energy sources and providing backup power during outages. 4. DC-DC converters. Application: Commonly found in power management for portable devices, automotive electronics, and telecom equipment. Function: They convert one DC voltage level to another, providing regulated power to various components. 5. Lighting applications. Application: Used in LED drivers and electronic ballast for fluorescent lamps. Function: Power MOSFETs regulate the current supply to LEDs or lamps, ensuring efficient operation and dimming capabilities. 6. Audio amplifiers. Application: Used in Class D amplifiers and other high-efficiency audio amplifier designs. Function: Power MOSFETs switch the audio signal efficiently, producing high-quality sound with low distortion. 7. Telecommunications. Application: Found in power amplifiers for RF transmitters and base stations. Function: Power MOSFETs amplify signals while minimizing distortion, improving communication quality in mobile and wireless systems. 8. Power distribution systems. Application: Used in circuit breakers, protection relays, and power management systems. Function: They help control and distribute electrical power safely and efficiently, protecting circuits from overloads and faults. 9. Automotive applications. Application. Used in electric power steering, fuel injection systems, and battery management systems. Function. Power MOSFETs manage power delivery and control for various automotive subsystems, enhancing performance and efficiency. 10. Renewable energy systems. Application. Utilized in solar panel inverters, wind turbine controllers, and energy storage systems. Function. They convert and manage power generated from renewable sources, facilitating grid integration and energy storage. 11. Consumer electronics. Application. Found in laptop power adapters, gaming consoles, and home appliances. Function. Power MOSFETs regulate power supply and enable efficient operation in a variety of consumer electronic devices. 12. Battery management systems. BMS. Application. Used in electric vehicles and rechargeable battery packs. Function. They manage the charging and discharging of batteries, ensuring safe operation and extending battery life. Summary. Power MOSFETs play a crucial role in a wide range of applications, enabling efficient power management and control in various electronic systems. Their versatility and performance characteristics make them indispensable in modern technology, from industrial applications to consumer electronics and renewable energy systems. Power MOSFETs offer several advantages that make them highly suitable for a wide range of applications in power electronics. Here are the key advantages. 1. High efficiency. Description. Power MOSFETs have low on resistance, R_S on, which minimizes power losses during conduction. Advantage. This leads to higher overall efficiency in power conversion and management applications, reducing heat generation and the need for extensive cooling. 2. Fast switching speed. Description. Power MOSFETs can switch on and off rapidly, often in nanoseconds to microseconds. Advantage. Fast switching capabilities enable high-frequency operation, allowing for smaller components and reduced size in power supplies and motor controllers. 3. High input impedance. Description. The insulated gate design results in a very high input impedance. Advantage. This characteristic allows for lower gate drive current requirements, leading to reduced power consumption and simpler control circuits. 4. Low thermal resistance. Description. Power MOSFETs are designed to dissipate heat effectively. Advantage. This property allows them to operate at higher power levels without overheating, increasing reliability and longevity in demanding applications. 5. Robustness and reliability. Description. Power MOSFETs are built to withstand harsh operating conditions, including voltage spikes and thermal stress. Advantage. This robustness enhances their reliability in critical applications, reducing the risk of failure over time. 6. Diversity in voltage and current ratings. Description. Power MOSFETs are available in a wide range of voltage, from 20 V to over 1000 V, and current ratings, from a few amperes to several hundred amperes. Advantage. This diversity allows designers to select MOSFETs that perfectly fit the requirements of their specific applications, making them adaptable to various power levels. 7. Simple drive requirements. Description. The voltage-driven nature of MOSFETs means they can be driven by simple voltage levels. Advantage. This simplifies the design of gate drive circuits compared to bipolar junction transistors, BJTs, which require continuous current to remain on. 8. Integrated protection features. Description. Many modern power MOSFETs come with integrated features like avalanche ratings, which provide protection against voltage spikes. Advantage. These integrated features enhance the safety and reliability of circuits, making them easier to implement in complex applications. 9. Versatility. Description. Power MOSFETs can be used in various configurations, e.g., parallel or in series, and are compatible with a wide range of topologies, e.g., half-bridge, full-bridge. Advantage. Their versatility makes them suitable for diverse applications, from power supplies to motor drives and renewable energy systems. 10. Low noise operation. Description. The operation of power MOSFETs produces minimal electromagnetic interference, EMI, and switching noise. Advantage. This characteristic is crucial in sensitive applications, such as audio amplifiers and communication devices, where noise can degrade performance. Summary: the advantages of power MOSFETs, including high efficiency, fast switching speed, high input impedance, robust thermal performance, and versatility, make them essential components in modern power electronics. Their design features facilitate their use in various applications, from consumer electronics to industrial automation and renewable energy systems, enhancing overall system performance and reliability. Power MOSFETs are an essential component in modern electronics, contributing to the efficiency and performance of devices that require precise power management and control.